In this chapter, we're going to talk about temperature and heat. We've talked a lot about the losses of energy due to kinetic friction. If you slide a book along a table, you give it some energy, it slides along and it finally comes to rest. Well, where did that energy go? Did we really lose it? We talk about whether mechanical energy is conserved or not, and that's a valid consideration, whether there are any non-conservative forces at work. But can we actually account for that heat, and where does it go? Or where can we account for the energy, and where does it go? As it turns out, the energy that is lost in that book sliding across the table is converted into random thermal energy of the molecules in the book and in the table. It heats up. The table heats up, the book heats up a little bit, and that's where the energy goes. So actually we can ultimately conserve energy even in non-conservative situations. So that's what these next few chapters are going to be about, temperature and heat. In this chapter, we'll talk about temperature scales, the Kelvin scale, the Celsius scale, Fahrenheit scale, linear thermal expansion. If you heat something, it expands. We'll talk about internal energy and temperature changes, specific heat capacity, and latent heat. That's the heat associated with a phase change. So if you, we were just trying to thaw out some shrimp the other day, and you take this frozen shrimp and put it in water, and then you mix it around a little bit to thaw the shrimp out. But the water gets cold very, very fast. There's a lot of heat associated with changing the state from frozen or solid to unfrozen. That's called latent heat. Okay, so temperature scales. Here is the two most commonly used temperature scales. The Fahrenheit scale that we use every day, how many degrees Fahrenheit, etc., etc. And the ice point, the freezing point, is at 32 degrees Fahrenheit, as you might well remember, because below 32 is below freezing. You might also remember the boiling point of water at atmospheric pressure, standard temperature and pressure, is 212 degrees Fahrenheit. Well, that's kind of an embarrassing temperature scale. I don't know who invented it. I guess a guy named Fahrenheit. A more useful scale, a little bit more tied to our natural phenomena in the world, is called the Celsius scale, where the ice point is 0 degrees. So when the temperature on the Celsius scale is below 0, that's below freezing. The same as saying that the temperature is below 32 degrees Fahrenheit. And 100 degrees is the high end, the boiling point or the steam point, where you can convert water into steam. And there's a 100 degree Celsius degree difference between the ice point and the steam point, whereas between 32 and 212, if you take 212 minus 32, you get 180 Fahrenheit degree steps. So the Fahrenheit step is a smaller step. Changing things by 1 degree Celsius, you change it quite a bit. How do you relate the two? And the answer is, given this information, which I think you've all maybe seen before, you can figure out how to convert a temperature in Fahrenheit to a temperature in Celsius. And first of all, what you want to do in order to get it right is you want to subtract that 32 off, and that's what you do. The temperature in Fahrenheit minus 32, and then you want to realize that a change in 1 degree Celsius is less of a is more of a change than so for any given temperature change in Fahrenheit, the corresponding change in Celsius is going to be less, because the degree in Celsius is more. So I don't know if that made any sense or whatever, but the conversion factor here, 5/9, that comes from the ratio of 100 degrees to 180. So 100 divided by 180, well, if you divide numerator and denominator by 10, you get 10 over 18. And then divide each by 2, you get 10 divided by 2 is 5, 18 divided by 2 is 9. So this is the ratio between the number of degrees between ice and steam for each of these two. So that's how this one comes out. And we could double check to make sure it's right. If the temperature in Fahrenheit is 32, then 32 minus 32 is 0, and the temperature in Celsius is 0. If the temperature in Fahrenheit is 212, we put that in here. 212 minus 32 is 180. And 5/9 of 280, as we just showed, is 100. So that gives you this 100 degrees here. So 5/9 TF minus 32. No big deal. I think you've seen this before. Just a couple of quick examples. A healthy person has an oral temperature of 98.6. What would this reading be on the Celsius scale? Plug it into the equation. T Fahrenheit is 98.6 minus 32 gives 37 degrees Celsius. This is a normal body temperature in Celsius. A bank sign indicates that the outdoor temperature is negative 20 degrees Celsius. Find that Fahrenheit temperature. Now, for this one, we need to solve for the Fahrenheit temperature. So how do we do that? We can multiply both sides by 9/5. And this 5 cancels that 5. This 9 cancels that 9. So now we have TF minus 32 equals 9/5 TC. And so we can add 32 to both sides and get that the temperature in Fahrenheit is 9/5 TC plus 32. Now you can memorize this equation if you want, but I think it's dumb to memorize that equation. I like to keep the number of equations I need to memorize down to a bare minimum and then just do algebra. You can do this algebra, it's easy. So we've just shown that T Fahrenheit is 9/5 TC plus 32. We're putting in TC is negative 20, and plug the numbers in, you get negative 4 degrees. Temperature scales are valuable in thinking about vasoconstriction. Infrared is used as a measure to measure temperatures. The temperature of different body parts. This is a demonstration of how your blood vessels constrict when you smoke. So your hands actually get colder. This is a demonstration of breast cancer detection, which can be detected by changes in temperature of tissues. And then this is a demonstration of El Niño heating. So these are ways of measuring, detecting temperatures in bodies. Ashley has 2 freezers in her laboratory. Inside freezer A, temperature is 0 degrees Fahrenheit. Inside freezer B, the temperature is 0 degrees C. Which one of the following statements about these freezers is true? So let's go back to this diagram. I think it's easiest to see. We can do the math, but in one case, the temperature is 0 degrees C, and in the other case, the temperature is 0 degrees Fahrenheit. So here's 212, here's 32. So 0 degrees Fahrenheit is going to be somewhere down here. 0 degrees Fahrenheit. Which one's going to be colder? Well, the 0 degrees Fahrenheit is below freezing. And 0 degrees C is at freezing. So the Fahrenheit is at 0 degrees Fahrenheit is going to be colder. And we could do it with the math too. So freezer B is 0 degrees C. Freezer A is 0 degrees Fahrenheit, and that one's colder. So that's the one that we want. So the same temperatures, no way, blah, blah, blah. Okay.